So where we're heading next is naming ionic and molecular compounds. So before we get there, we're going to have a lesson reviewing the periodic table and talking a little bit about bonding and why we have these two distinctive set of naming rules. So starting off with the periodic tables, grade 10 students absolutely have to be familiar with the term groups and periods. So groups are vertical or columns. So we have group 1, we have group 2, we have way over here group 13, or if you skip the transition metals, 3A. So we don't use the transition metals a lot in one of the numbering systems that's used a lot, particularly in 10 and 11 chemistry, skips these transitions. So we get 3A, 4A, 5A, 6A, 7A, and then finally 8A. Now, many of these groups have very similar chemical properties, and they get names. So the alkali metals in group 1 are all really reactive. The alkaline earth metals are quite reactive metals, but not quite as much. You see the halogens of similar properties and their ions of similar properties, and the noble gases or inert gases all being quite unreactive. So because of similar chemical properties, we've named the vertical columns for many of the groups. They don't all get names. If we look at something like group 4A, we've got carbon, which is a nonmetal. Then we've got the zigzag lines. We have some metalloids around the zigzag line, and then we have some metals at the bottom. So metals, metalloids, nonmetals. We don't have a name here because we don't have consistent chemical properties like we do in 1, 2, 7A, and 8A. Now, periods go across. So our first period, our second, our third. Now we don't have names because we have total extremes from side to side. Sodium is super reactive, really likes to lose electrons, where we have chlorine who really wants to gain electrons, and then we've got a noble gas. So we don't have any similarities across periods, so we don't have any names. But we got metals on this side. And we've got our nonmetals over here. And this will be super important for determining whether something is ionic or molecular and how we should name it. And then we got this zigzag line, which I'm roughly approximating with a diagonal that separates nonmetals and metals. So one skill that's used a little bit more in Chem 20, but it's really nice to introduce now, and it really gives us a clear indication of our bonding, is electron dot diagrams. The periodic table will tell us the total proton and electron count of all the atoms, but what we really just care about is the outermost electrons. And that's what electron dot diagrams do. They just show the valence electrons, which these are the outer electrons. And there's a shortcut. Let's look at this with a Bohr model of boron, and then we'll look at the shortcut. So there's boron, atomic number 5. So it's going to have 5 protons. And when it's neutral, the electron count would also be 5. So it would go 2, 8, 8, 8. So we put 2 electrons. We've got 3 left. 1, 2, 3. And it turns out these inner 2 really don't do anything in terms of bonding. We just care about these 3 outer ones. So an electron dot diagram would just put 3 dots around the boron to represent the 3 electrons that really matter. Now, the really straightforward pattern to predict this outer ring's electron count is just the group number. Everything in group 1 will have 1 a dot in its electron dot diagram. Group 2, 2, group 3A, 3, 4A, 4, 5, 6, 7, and our noble gases nice and full out of 8. Now there are some quirks to this. As you get deeper in the transition metals, other things happen, but for Science 10, Chem 20, and even Chem 30, grade 12 Chem, this is a pretty good model that's going to get you through. So we can quickly do a few examples. So the electron dot diagram just has the symbol in the middle, and then the dots representing how many valence electrons are around it. So fluorine is in group 7. We don't care what the atomic number is. This is neutral. We don't care what the charge, just group 7. So it's got 7 dots. Now they come in 4 pairs, and we represent them by top, bottom, right, left. So there's 1 electron, 2, 3, 4. 5 makes a pair, 6, 7, and then we run out. So that's the electron dot diagram of fluorine. So fluorine is missing 1 dot. So it somehow either has to share or steal an electron to fill that hole in. And that'll lead to the 2 types of bonding. If we look at a fluoride ion, this is now fluorine, but it's gained an electron. And this is where our table tells us what the charge is. You don't have to memorize it. So we have a fluorine atom with 7 valence electrons, but now we have to do the negative ions have gained an electron, positive have lost. We have to add 1 more. So where there were 7 normally, the fluoride ion will have 8. 1, 2, 3, 4, 5, 6, 7, 8, and that filled it up and it's nice and stable. Now one thing you have to do is square bracket any ions. That's something you'll do in Science 10, Chem 20, and Chem 30 when you do this type of notation. So the square brackets in the charge just means somewhere in here is the extra electron. We don't know exactly where it is, but somewhere in here has an extra electron because it's 1 minus. If it was 3 minus, then somewhere in here would be 3 extra electrons. Let's look at a couple metals. So if we look at sodium, so we'll do the neutral first. Sodium is in what group? It is in the first group. So that's going to be quick. 1 dot. This is what makes it so reactive, and everything in this whole group is going to have 1 dot. So whether it's sodium that I did, or if we looked at lithium, same group, same electron dot diagram. If we look at the sodium ion, it's going to be 1 plus. I'll jump ahead and throw in the brackets so I can write my charge. 1 plus means we've lost an electron. So we have 1 dot in the atom, we've got no dots in the ion. So that outer energy level has been emptied. So that's it, there's no dots. So where we're going to lead to this is if you have something like a metal with 1 dot that wants to lose its dot, and something like a fluorine atom that wants to gain 1, you can get a transfer here. And when you get a full transfer between a metal and a non-metal, you get ionic compounds and 1 set of naming rules. If you don't have a metal and a non-metal, you get sharing, and that leads to the other set of rules that you hopefully saw in junior high and are going to be expanded upon in grade 10. So let's dive into these 2 different types of bonding. Some of this is Chem 20, so you don't have to know everything here, but you do have to understand ionic versus covalent. So in ionic bonding, you've got a metal with a few electrons to lose, plus you've got a non-metal that needs to gain a couple. So you could have something like sodium, which is in group 1 with 1 dot. With iodine, it's in group 7A. So we just care that that's going to lead to 7 dots. 1, 2, 3, 4, 5, 6, 7. I kind of put them in a weird order, but it doesn't matter. We have pair, 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 and a single. So what's going to happen is this missing electron in the iodine can be taken from the sodium. So this is going to lead to an ionic compound between a metal and a non-metal. Then we're going to get sodium with no dots left. So this is going to be 1 plus. And we're going to get iodide that used to have 7 and now has 8. And we can use these charges to balance the count of each. +1, -1, we only need 1 of each, and we don't write 1. So this is ionic bonding, metal and a non-metal, a full stealing. When you use prefixes is when you have covalent bonding. Now, this type of bonding is thoroughly discussed in Chemistry 20, so what I'm about to do is not something you'd ever be asked to do. But when you see two nonmetals you need to know this is when you're going to have sharing and a different type of bonding. So a little preview of what you'll end up doing next year is if you have carbon dioxide, you might get a hint that the carbon is in the middle, and then you could use your dot diagrams to figure out how this is going to be shared and put together. So oxygen is in group 6. So 1, 2, 3, 4, 5, 6. And our carbon is in group 4. And we're going to see something very different. We're going to see two singles shared. So this single and that single can come together and form a shared bond. This single and that single can come together. They're not being stolen, they're being shared. And we can get another sharing here and another sharing of this single and that single. So it's not stealing, it's sharing. And you get carbon with not one, but two sets of singles. So next year you'd put a double line or a double bond. And over here we've got not one, but two sets of single sharing. So we have a double bond. And this is carbon dioxide. And we only see these prefixes when we have sharing. And the next lesson we'll go through ionic bonding first and the sharing covalent bonding second, and we'll go through all those prefixes that you need to know, and should be on your formula sheet most likely, depending on your teacher.